Welcome back. Our next speaker is Professor Aditi Sheshadri. She's a faculty at Stanford University. She'll be talking about machine learning-based parameterizations. Aditi, thanks a lot for coming all the way.
Okay, thanks very much. I'm going to be talking to you about using ML-based methods, or in general, data-informed methods for SGS parameterizations. I'm going to be kind of focused on atmospheric gravity waves because that's the thing that my group has been focused on for the last couple of years. But I hope that the methods in general ought to be very generalizable. So you should be able to use something like this for ocean eddies or convection, cloud parameterizations. Pretty much everyone is working on convection and clouds right now. So that was one of the reasons that I decided not to do that. So this talk is going to be focused around atmospheric gravity waves, but I'm going to be talking in general about ML methods and how they can be used for SGS parameterizations. So let me just get into it. I have quite a bit to get through, and I'm going to try and do it in an hour. So I'm just going to jump into it. So in general, why do we need subrascale parameterizations? There's two reasons in general why we need them. One is that the process of interest is too small or fast to be explicitly resolved in a global climate model. So the current generation of GCMs typically have like a grid box of 100 by 100 kilometers. Sometimes they could be 50 by 50 kilometers. I've heard of 25, but not too much more than that. But then if you think of convection as an example, you have fast convective plumes, which are very much smaller than 100 by 100 kilometers, right? And then you have clouds, and I'm going to be talking about atmospheric gravity waves. Many such processes exist. And this is a problem that is going to be a problem for our lifetimes, probably our children's lifetimes, because computation is just not going to catch up to the extent that we need. So this is one reason why completely fluid processes have to be parameterized. Of course, clouds are very much more complicated than that. They can be a multi-phase problem. But just the fluid dynamics itself requires a turbulence parameterization, which to explicitly resolve, you've got to go down to some extremely tiny length scale, right? So this is a problem. We are all going to have a job for quite a while because of problem A. Problem B is potentially a somewhat more challenging problem, which is that no descriptive equations of the process exist. So if you think of biogeochemistry, soil moisture, things like that, we may not even be able to write down a set of equations describing the process of interest. And so these are the two common ways in which the need for SGS parameterizations arise, right? And I'm going to focus on three ways in which machine learning or data-informed methods in general could help with this problem. The first is when you take your subrascale parameterization, you throw it out the window and you replace it with a completely ML-driven algorithm, such as a deep neural net or a UNet or whatever favorite algorithm it is that you want to replace your subrascale scheme with. That's the first one. In the second one, which I actually really like, you can use machine learning or data-driven methods in general to calibrate an existing physics-based scheme. So if you have, for instance, an equation which you think is valid in this climate, it is going to be valid in a future climate, valid across all climates. But there's a bunch of constants or parameters in that equation which have to be basically fit based on available data, based on macrophysical climate parameters, such as you want the jet to be roughly in this region, or you want the QBO or the MJO to have an inherent period of interest to be some number, something like that. So if you want to calibrate an existing physics-based scheme using large data, or you want to calibrate it using macrophysical climate states, so you want the climate to look kind of right, that's one potential use. The other use that I've also become quite excited about in the last couple of years is to quantify uncertainties. And this can mean a whole lot of things, okay? The most common thing that it could mean is to quantify uncertainties associated with these choices of parameters and approximations in these SGS schemes. So for instance, you pick the entrainment rate to be X based on something, right? What does that mean for projections of extreme rainfall? So for instance, if you're interested in monsoon extremes and you picked your entrainment rate to be something, supposing the entrainment rate was not something, but it was something plus 0.2, right? What does that tell us for the statistics of extremes of monsoon projection going forward. So that's kind of what I mean by quantify uncertainty. So you want to include uncertainties in your climate prediction, or climate projection is a word that I like better going forward. And you can use ML to quantify uncertainties in existing physics-based SGS schemes, or you can also do it with completely ML-based SGS schemes. So I'm going to use the atmospheric gravity wave problem to talk you through examples of each of these. I'll try and spend about 15 minutes per problem, so it's going to be a 45-minute talk. And at the end, we can talk about questions, but then I'm also going to try and put in some exciting tidbits of ongoing research in my group on all of these problems. If you have questions, just like yell at me, put your hand up, whatever, and we can go through the questions. So since the talk is going to be focused around atmospheric gravity waves, I thought I would have a couple of slides on what these atmospheric gravity waves are and why they're important and why they're a source of uncertainty. So atmospheric gravity waves, for the physicists in the room, these are not gravitational waves. I'm not talking about ripples in space-time. What I am talking about is buoyancy waves. So whenever you have flow over a mountain, or you have flow over land and ocean, which can heat up to different extents, or convective systems can be a huge source of atmospheric gravity waves. The monsoon is a huge source of gravity waves. So atmospheric gravity waves are ubiquitously excited everywhere on the Earth. They form from a number of processes: flow over orography, moist convection, which everyone here should be very familiar with, geostrophic adjustment of jets, eddy-eddy interactions, unstable shear, lots of things. So they're mostly forced at the surface of the Earth. They propagate huge distances, both in the vertical as well as in the horizontal. So in the horizontal, they could propagate thousands of kilometers. And at some point, they break, just like waves break on the beach, and they deposit momentum. And these atmospheric gravity waves, are a really lovely example of the multi-scale nature of GFT, because they can exist over a large range of length scales. They can be 1 meter long in wavelength. They can be thousands of kilometers long in wavelength. And they also have a corresponding wide spectrum of frequencies. So, but much of the spectrum of atmospheric gravity waves is unresolved in a climate model. So it's a really lovely example of how a really small scale process can impact the planetary scale, because, for instance, they are thought to form a significant part of the budget of the jet stream, which is a planetary scale phenomenon. They're really crucial in stratospheric dynamics, which are close to my heart. We think that they play a significant role in setting up the QBO, which I'll talk to you a little bit about. Sudden stratospheric warmings. They're really crucial in cloud formation, so polar stratospheric clouds, subtropical clouds, which also are a pretty large source of uncertainty in climate projection. So they're an example of a really small-scale process which have a really big impact. So here are some Hofmüller diagrams showing you these fluctuations because of atmospheric gravity waves. This is pretty much at the equator. 60 hectopascals, pretty high up in the atmosphere. And you can see these tiny little fluctuations because of atmospheric gravity waves, both in U and in V. This was meant just to show you that there's a region where these waves can break, and where they break, they provide a forcing on the flow. So it's a very nice wave-mean flow interaction problem. It's also a very nice wave-wave interaction problem, because planetary scale Rossby waves and atmospheric gravity waves have interesting interactions. Talking about the modeling a little bit, these atmospheric gravity waves are generally not well observed. I mean, we have some satellite observations, but not great observations. So we don't have good observational constraints on what these waves are doing. And they're not particularly well modeled. So atmospheric gravity waves are parameterized, by which I mean that some guess at what the atmospheric gravity waves are doing in a grid box is put in based on the large-scale variables that are resolved. The existing atmospheric gravity wave parameterizations, all of them, suffer from a whole number of approximations and limitations. The biggest one is that all atmospheric gravity wave schemes are single column, by which I mean that these atmospheric gravity waves are only permitted to propagate straight up. No horizontal propagation of atmospheric gravity waves is permitted in any climate model. Many of these atmospheric gravity wave parameterizations don't have good observational constraints, as I talked about. I'll tell you a little bit about some very new observations that we are dealing with at the end of the talk. And another problem is that atmospheric gravity waves depend on under-resolved sources such as convection, which is itself parameterized. So it's quite a challenging problem. Atmospheric gravity waves are hugely non-local. So convection is also non-local, but if you expand your definition of a column a little bit, you're doing not too badly, right? But atmospheric gravity waves can travel from an island in the Pacific all the way across the world and deposit its momentum thousands and thousands of kilometers away. And models just don't have that. So,
ask a quick question.
Yes,
so,
sure.
So when you say the gravity wave, these are non-breaking gravity waves, right? This is before breaking. Is that right?
So they force the mean flow when they break.
But the parameterization is for...
The parameterization is for the effect of the breaking.
Only for breaking?
Only for breaking.
For the non-breaking waves, are they resolved then?
No. But
maybe you need them only when they break.
Right. So the way that they force the resolve flow is by breaking. So the atmospheric gravity wave schemes focus on that. The generation and propagation is kind of assumed. I'll talk about one of these parameterizations in a second. Here's an example of just how bad the situation is. So what we're looking at, so this is the Canadian climate model, but I don't mean to focus on them. About every other model will be similar. So what this is the 4 times CO2 response of this model with 2 versions of an atmospheric gravity wave parameterization, which are indistinguishable from each other, meaning you don't know whether one model is better than the other based on just observational constraints. And this is the change in sea level pressure over the Arctic in these 2 different atmospheric gravity wave schemes, and this is the difference. So you can see that there's a huge change in the surface phenomenon, surface pressure, because of just these tiny changes to the atmospheric gravity wave parameterization, both of which are equally valid, right? So this is a huge source of uncertainty in tropospheric processes, which we care quite a lot about. So this was the problem, and I started working on this a few years ago, and I wanted to come at it from a number of different perspectives, and a couple of very nice projects have coalesced around this problem, and I'll tell you about both of these in a little bit. So since this talk is going to be based around ML, I'm going to be talking about one of the first completely ML-based gravity wave parameterizations that we developed a couple of years ago. And the nice thing about this is that we coupled it back into not a full global climate model, but sort of an intermediate complexity climate model. It has a full atmosphere in it, so it's not too bad. And it is coupled and it is stable. It is running online. So I'll talk about this. And then I'm going to talk about uncertainty quantification, calibration and uncertainty quantification for both physics-based atmospheric gravity wave parameterizations, which currently exist, and completely ML-based, this parameterization that I'm going to be talking about. And then I'll show you some really exciting new stuff, very high resolution simulations, new observations. So this is the outline for the talk. So let me jump into it. So when I got into this problem, the first thing that I wanted to try was, can we throw out a simple gravity wave parameterization and replace it with a neural net? So that was the initial thought. This is a couple of years old now, but this paper has been extremely well received because it was online. It was coupled to the climate model. We used somewhat of an idealized model. It's called MEMA, model of an idealized moist atmosphere. It has everything that we need, but not too much more. It has RRTM radiation, interactive water vapor. It's not the highest resolution model. It's 2.5 by 2.5 degrees. But it gets the job done, 40 levels in the vertical. And the important thing is it has implemented into it this Alexander and Dunkerton atmospheric gravity wave scheme. And Alexander and Dunkerton is widely used. It's used in the GFTL model. Variations of it have been used in various state-of-the-art climate models. And it's a nice scheme. It basically mimics the time and space average effect of many of these discrete intermittent gravity wave packets by just adding a forcing term in the zonal and the y direction. So it just adds a drag in x and a drag in y. That's all it does. And it is single column. At the very end of the talk, I'll talk about a completely non-local parameterization. But to begin with, we had to start somewhere. This is a single column parameterization. Gravity waves are assumed to be forced at the surface of the Earth. They just go straight up and they deposit drag at some point. That's all it is. So we started off with a simple neural net, simple-ish neural net. It's quite deep. We threw at it all of the variables that we thought might be interesting: zonal wind, meridional wind, vertical wind, temperature, height, latitude, longitude, and the surface pressure. All of these things don't seem to matter all that much, but we started off with all of these things. Here's a schematic of the architecture. If you want details, it's all in this paper. This was done by a master's student at Stanford, by the way. He was just exceptional. He is now a PhD student at UW. Unfortunately, he decided not to stay, but it's a lovely paper, I think. I'm showing you 3.8 million trainable parameters, but you don't need that many. There's a complexity analysis in the paper, and you can get away with about 500,000. Does a pretty good job. And the good news, so we call this, we had to come up with a name for this neural net, so we called it WaveNet, because why not? So here's the zonal gravity wave drag from WaveNet on the left. This is the physics-based 89 parameterization on the right, and the difference is in the center. This is for the Y drag, and as you can see, WaveNet is doing a pretty good job. I'm showing you an animation here because I like animations, but its offline accuracy is actually incredibly good. So that's good news. We care a lot about the QBO in the tropics because the atmospheric gravity wave scheme is crucial for the presence of a QBO. So the QBO is the right thing to look at to see if we're doing a reasonable job. What I'm showing you here is the zonal gravity wave tendency from the physics-based parameterization on top and WaveNet at the bottom. You can see that WaveNet is sort of over-predicting drag a little bit in certain positions, but we fixed this problem subsequently. This was for the first paper. And then just telling you a little bit more about WaveNet. Here's some feature learning experiments. That's what they're called. That's when you put in different subsets of your input variables to try and figure out exactly which ones are important. We also did a Shapley value analysis to try and make sense of it from a physical perspective. So what I'm showing you here is the drag as a function of pressure. This is R squared compared with 8099 itself. And here's the zonal gravity wave drag column averaged R squared, and this is the Y direction. And so all of these different colors are different combinations of input parameters thrown into WaveNet. So to cut a very long story short, I'll just tell you that all you need to get the drag in the zonal direction is you need the wind in the zonal direction, and similarly, if you give it V, you get the Y drag pretty well. And this kind of makes sense if you think about the polarization relationships. All you really need for a simple parameterization such as 8099 is to specify the winds, right? Because the waves are propagating through a background wind profile and depositing drag when they should be depositing drag. So that's pretty much all it is. One reason that this is doing so well is because 8099 is so simple, okay? So you shouldn't be too impressed. But the WaveNet does pretty well, and if you just give it U and V, you're doing reasonably well. Okay, so that's all great. That was all offline results. Much of the difficulty of integrating ML schemes with existing climate models is actually from an engineering or a computing perspective, right? So all ML algorithms are in Python. I mean, well, you can write them in other languages, but you tend to write them in Python. And all global climate models are in Fortran. So coupling an ML scheme in Python with a global climate model in Fortran is way more effort than it should be for a PhD student or a postdoc, right? So the first attempt that we threw at this was just an interoperability package called 4Pi, and it works. Okay, so here's the QBO. What I'm showing you on top is from 8099. So this is the model with 8099 implemented into it. So then we took WaveNet and we threw out 8099 and put in WaveNet into the model and ran it online for hundreds of years of integration. It is stable and accurate when coupled online. And here's the QBO. It just felt sort of magical when it worked. So MIMA now calls WaveNet for every time step, but it needs drags because of atmospheric gravity waves. WaveNet provides the drag. Fortran and Python are talking to each other, no problem. It is stable, it is accurate, and we have hundreds of years of integration. The period of the QBO that I'm reporting here is a little bit off, but this can be fixed with different training. We actually tried to do this giving WaveNet only 1 year of data. So it's only seen one phase of the QBO, it had not seen the other. So it's doing really, really well. The other piece of good news from this initial paper was that WaveNet generalized pretty well. So these polarization relationships ought to, of course, they hold in a different climate. And so the Shapley value analysis would indicate that WaveNet should also generalize reasonably well. It does. I won't dwell too much on these results, but what I'll show you is the bottom panels. So this is the 4 times CO2 response of the large-scale circulation of the atmosphere. This is 8099. This is the response. So it's the 4 times CO2 minus the control with 8099, and this is with WaveNet. So you can see that WaveNet gets some things a little bit wrong. The intensification of the polar vortex in the northern hemisphere all the way through the depth of the stratosphere isn't quite as strong with WaveNet, and there's some interesting differences in the tropics as well. But overall, the poleward shift of the jets and the polar stratospheric response is captured reasonably well with WaveNet. So this was sort of a first proof of concept, almost success story of throwing out a completely physics-based parameterization and replacing it with a completely neural net-based parameterization. Of necessity, it is somewhat simple because 8099 is simple and WaveNet as well is rather simple. But the fact that it works, it is stable and accurate when run online gave us some confidence to keep going down this path. Where we are now is that, I'm not going to show you much from this, but where we are now is that we have good ML parameterizations for every gravity wave parameterization in WACM, which is a state-of-the-art climate model. We're working on coupling it back to WACM in a way that isn't too computationally absurd. So FORPA, this interoperability packet that I discussed slows down your model quite a bit, and no one will run with a slowed down model. So we're attempting to implement these ML schemes into WACM, which is NCAR's model, in a way that is feasible to run computationally. And it seems like we're getting there. If you invite me back next year, I'll show you some results from that. This is Zach. He did all of this lovely initial work. He's now a PhD student at UW, and will probably, well, he's not graduating anytime soon, so we'll get to that. Okay, so I'm going to, when did I start? 11:50 something, right? Okay. I'll talk about uncertainty quantification. I'm going to start off with uncertainty quantification of 8099, which is now a parameterization that you've heard a little bit about. So what do I mean by uncertainty quantification? I'll just say it again. Modeling centers will pick a number for a parameter based on something that they want to optimize, like they want the climate to look right, or they want the drag to be a certain amount, something like that. So they pick one parameter, right? And it's usually manually tuned. It is not a systematic process of calibration. So what we would like is to carry through probability distribution functions of everything, right? We want PDFs of the parameter, of the prior estimate, the posterior estimate, and PDFs of the climate output. So that is what we would like. So I'm going to show you a couple of ways to do this. I'm going to focus on 8099, and I'll tell you a little bit more about 8099 now for that reason. 8099 launches a spectrum of momentum flux as a function of phase speed of the waves. You don't have to know too much about this, but that's what that looks like. And it also accounts for intermittency, meaning waves are not launched all the time. There's a particularly large event, for instance, if there's a huge gust over a mountain, then you expect huge momentum flux, right? So that effect is parameterized through an intermittency factor here that I'm showing you. And the two crucial parameters in 8099, one is this BT, which is the total gravity wave stress, and the other is this parameter CW, which is a half width of phase speeds. So it's a Gaussian, and it's got a half width of phase speeds, and we want the total gravity wave stress. And both of these are not well constrained because we don't have good observations. Given that we don't have good observations, we are going to try and constrain these parameters using the QBO. So I mentioned the QBO in my first lecture back last Monday or something. And the two features of the QBO that we would like to get right are the period of the QBO and the amplitude of the QBO. So here's our inverse problem. Y here you could think of as being the two things about the QBO that we want to get right, the period and the amplitude. You could think of this G as your forward model. So I'm going to stick with 8099 and I'm going to stick with NEMA. So G here is our forward model. And the thetas, these parameters that we want to optimize, are these two things that I mentioned, the half width and the total gravity wave stress. So any climate modeling center would have to assign a value to CW and assign a value to BT based on something. So what we would like to do is to get a distribution of plausible values of CW and BT based on these two output features of the QBO. Is that clear? None of the students are nodding. So yes, no, yes, okay. Let me move forward. I'm going to tell you about two ways to do this. One is a family of ensemble Kalman methods, and the second that I'll talk about is a family of Bayesian methods. I'll talk about ensemble Kalman inversion to begin with. This is a set of papers that came out of Tapio Schneider's group a couple of years ago, and we're going to follow it through and see what it does with our atmospheric gravity wave parameterization. The first step is the so-called calibration step, which is we're going to use a process called ensemble Kalman inversion to try and push these parameters to give us a desired output. So the output is the period and the amplitude of the QBO. The parameters are the two parameters that I mentioned here, CW and BT. Following the calibration for the uncertainty quantification step, we're going to build a Gaussian process emulator, which is basically a method that is trained on the output of your model to tell you the output of the model based on these parameters, okay? I'll talk more about that. And then we're going to sample this space to get a bunch of plausible parameters, basically. But let me talk you through this, and we'll go through it one by one. So the first step is this calibration step using ensemble Kalman inversion. What I'm showing you here is an animation of each iteration of ensemble Kalman inversion. I'm showing you 10 iterations. And what we want to do is push the model to look like what we call the truth. Now, the truth can be whatever you want. It can be observations of the real QBO. It can be a very long model integration. It can be whatever you want. So to begin with, we use a very long model integration since it gives us very good statistics. So we want a period of the QBO and an amplitude of the QBO to be these numbers that we got from the model. And then with every iteration of ensemble Kalman inversion, we launch an ensemble of NEMA runs. At each iteration, we launched 20 NEMA runs of 10 years of integration. And what I'm showing you here is the convergence of the ensemble Kalman inversion. Ensemble Kalman inversion technically converges at infinity. So at some point, you just have to call it. So what I'm showing you here on top is these parameters, CW and BT. And at the bottom is the things that we're trying to optimize, the period of the QBO and the amplitude of the QBO. The nice thing about this is that you can also take one standard deviation of the process through the entire method. So you can see these parameters are being pushed closer and closer to numbers that give you something like a QBO period and QBO amplitude that is desired. That's what I'm showing you here. The next step is to build this emulator. The emulator is trained on the same model integrations which were set forth in this process. So if you have 10 iterations with 20 model integrations each, you have 200 runs that you can train on. We trained on, I think, 150 runs and tested on the rest. So this is the test, this is the QBO period, and this is the amplitude. What I'm showing you here is the output of the Gaussian process emulator versus the actual model. So if the emulator is doing a pretty good job, it should lie on this one-to-one line, which it kind of does. So we say that the emulator is doing a reasonable job. Having done that, we can now use this emulator to build up basically it's not a theory, but it's what the emulator says is this relationship between these parameters, the CW and the BT, and the things that we're trying to optimize, the period and the amplitude of the QBO. So here's these lovely contour plots with no breaks in between them. And this is not coming from, 700 runs or something. This is just coming from 150 of them. And the rest is being filled in by this emulator. As I said, you can also carry through a standard deviation. That's what I'm showing you at the bottom. Having done that, we can now use a standard random walk metropolis to sample in the region where we want the period and the amplitude to be. So this is showing you the path of the MCMC. It is going around the region of this phase space where the period is around where we want it to be and the amplitude is close to where we want it to be. Having done that, we can now build a lovely 2D histogram. This is what this is. This is a posterior histogram of the CW and the BT, which gives us statistics of the QBO, which are now matched to what we want them to be from this long model integration. I'm also showing you conditional histograms of CW and BT, top and bottom. This is integrated across one variable. This is all the work of Laura Mansfield, my postdoc. And this is given some interesting results, right? For instance, it is telling us that the QBO features are not all that sensitive to what you do with the half width of the phase speeds, because here's the prior distribution, here's the posterior distribution, it's not that different. However, if you look at the BT, here's the prior distribution, here's the posterior distribution, so it's narrowed quite a bit. So it's telling us that there's only a pretty narrow range of values of BT, which gives us a QBO that we want. Now, having done all of this, we can sample CW and BT from this 2D histogram, and we can now do really nice uncertainty quantification because we can run MIMA forward with CW and BT sample from this 2D histogram and see what is the range of QBO responses that we can get in a double CO2 or a quadruple CO2, like whatever forcing you're interested in. And because of time, I won't go into it in too much detail, but the uncertainties because of these parameter choices can be quite large. This is called parametric uncertainty. So this is a nice way to actually carry through uncertainties in climate projection. Any questions before I move on to Bayesian methods? Yes.
Of non-stationarity.
Yes.
Is asked. I mean,
Yes.
How is that addressed here?
Yeah. So it is addressed using this. Okay. So one of the issues with ensemble Kalman inversion coupled with the Gaussian process emulator is you're assuming everything's Gaussian, which is why I'm going to talk about Bayesian processes next. But the way that it is addressed is that you carry through these standard deviations. So the period of the QBO is not just 28 months. It is 28 months plus or minus some standard deviation. The amplitude of the QBO is not just whatever, it is plus or minus whatever. So that's how it's addressed. You could do it maybe potentially better with Bayesian processes. So let me talk about those. Here we are. This is another whole family of methods called approximate Bayesian methods. It also requires the development of an emulator of your model because too many forward model integrations are too expensive, right? And I'm running MIMA. You want to do this with a fully fledged climate model, it's going to be really expensive. So this emulator is kind of crucial. And approximate Bayesian methods do this in a different way. They don't really do a calibration. Like you don't get a point estimate of your parameter. What you end up getting is a plausible region of space. So you end up getting, so you start with a prior. You have statistics of observations. And what I'm going to show you now is actually observations, not a long model run. You have your observations, you have a prior, and then you use your emulator, and with every iteration, you narrow down plausible regions of space. That's what approximate Bayesian methods do. I won't go into too much detail, but here's an animation. So if your observations here, Z are your observations. F here, this thing is your emulator. And you have some unknown true function that you're trying to approximate. You can calculate what Bayesian stats people refer to as an implausibility, or what they call an NROI space, a not yet ruled out space. I've always thought of that as a little bit funny, but that's what it is. So if I play this again, you can watch you can watch that we're starting off with some uniform prior, you build your emulator, and you try and get closer and closer and closer to your unknown true function by updating your implausibility or your not yet ruled out space. It's a bit hard to go into too much detail in a talk like this, but I'm happy to share the paper. This is the work of my student, Rob King. So here's some results. This is the same problem that I've been talking about, 8099, with your CW and BT as the parameters that you want to optimize, calibrate, whatever. Here is this implausibility or the not yet ruled out space that comes in. The method that we're using here is called Bayesian history matching. So what it does is that it tries to match the statistics of observations with the statistics of your model output. It doesn't require too many forward integrations, at least with these two parameters. We're doing reasonably well. And the end of all of this is that it seems like with Bayesian history matching, we can get a more compact posterior distribution than with ensemble Kalman inversion with an emulator. So this is a very recent paper, just came out. Here is the posterior distribution of plausible parameters. This is CW and BT again, CW and BT again. And this is now done against observations, real observations of the QBO, along with the variability of the real observations of the QBO. So it seems like Bayesian history matching or Bayesian methods in general give us a more compact posterior distribution than ensemble Kalman inversion or ECI with an emulator. Rob is currently working on trying to break both of these methods by throwing at it increased dimensionality, increased, more complex runs, more things to optimize, things like that. So again, if you invite me back in a year, I'll tell you which one breaks under what circumstances and which one is best to optimize which dimensionality of parameters. So this is about calibration and uncertainty quantification for a completely physics-based parameterization. The equations are valid in any climate. It's just these parameter choices that have to be tuned or calibrated based on existing climate or features of the existing climate. How much time do I have left? 20 minutes, great, okay. Wonderful, so I'll take 10 minutes on this other one and then let's see. I also wanted to talk about uncertainty quantification for purely ML-based subgrid scale parameterizations. So I'm gonna, let's go back. What am I doing? So I'm gonna stay with this wavenet in MIMA, which I introduced at the beginning of the talk. This is this Alexander and Dunkerton parameterization, same deal, and we're using Zach's wavenet. But we're doing it in a slightly different manner. So these are, I believe they're called deep neural nets or an ensemble of neural nets. So in the place of training just one neural network, what we did was take wavenet, but then train the same neural network 30 times with different initializations, slightly different initializations. And so the weights of the of wavenets 1 through 30 will be slightly different. I believe the first paper on something like this is this one back in 2017, but you never know, you might find something even earlier than that. And here's what results. So again, this is online. So here are the offline estimates. The true drag from 8099 is the black line. The online mean, the offline mean is this blue line, and the offline one standard deviation between these 30 wavenets is in the blue shading. So this is all offline, it's pretty good. Offline accuracy is incredible for all 30 of these. However, if we take these 30 different neural nets and couple them online, you can see that they're really, really large uncertainties because of these different weights of the 30 different neural nets. Need progress, yeah. And each of these different neural nets have different QBOs, even though the offline accuracy is very, very similar. So what I'm showing you here is 8099 on top. Here's one neural network, two neural networks, and three neural networks. I have a plot at the end with, I think, 10 different QBOs from these 10 different neural networks. They all look different. So the period is different, the amplitude is different, the standard deviation of the period is different, the standard deviation of the amplitude is different. So when you're doing something like this and you're replacing a standard subgrid scale parameterization with a completely machine learning subgrid scale parameterization, you have to be aware that there's inherent uncertainties associated with the weights in these neural nets. Here's just summing up what I showed you in some numbers. These are I've been told these are called violin plots. I think that kind of makes a little bit of sense, but that's what they are. This is AD99. This is this ensemble of neural nets. Basically, there's increased QBO variability because of poorly constrained parameters. So this is parametric uncertainty again. But then there's also model error. Why? Because you're coupling these neural nets back into the model. The drag influences the wind influences the drag. And so if you're doing something wrong in the model itself, the parametric uncertainty and the model uncertainty couple together, and you get very different results. So I'm not going to claim this is the first paper that's done this. Again, it's hard to say. I mean, I'm sure somebody else has done this, but we weren't aware of somebody else having done this. So this just came out again in James. The take home is that there's a big difference between training a neural net offline and getting very, very, very good accuracy and then coupling it online. Your uncertainties are huge. They can be quite significant. Okay, so I wanted to talk a little bit about sort of ongoing work in my group. This is all published work. I wanted to talk a little bit about ongoing work in my group about how do we actually tackle this problem, right? Because atmospheric gravity waves are immensely complicated. As I said, they're a really lovely example of the multi-scale nature of GFD, and their highly non-local nature makes it quite interesting. It's been a challenging problem. This talk is not meant to be about observations, it's meant to be about ML, but I wanted to talk a little bit about using some very new observations in ML schemes or in calibration. Can I see a show of hands? How many people have heard of Loon, Project Loon? That's not fair. You've been to previous talks. But okay, so Loon came out of, it was a Google project. It was a Google X project previously. So it started in 2013 or 2014 when they were putting balloons into the upper atmosphere, so the upper troposphere, lower stratosphere, to provide internet to everyone below. They started off in New Zealand in the Southern Hemisphere. And they shut down in 2021, but between 2013 and 2021, they had about 1,000 balloon flights in the upper atmosphere, and they just happened to measure the location, the temperature and pressure about every 60 seconds. In some cases, it's even more than that, about every 30 seconds. And I decided I really wanted to get my hands on this data. I probably spent 1.5 to 2 years just bugging everyone that I knew to give me access to this data. And finally, I got my hands on it. The data is rather messy, as you can imagine. This is not a scientific ballooning campaign. For scale, if you were to put about 12 balloons into the stratosphere for a few months, which is, there have been scientific ballooning campaigns of that order, about 10, 12 balloons for about a month or two. There have even been campaigns that have gone for about a year. The cost of something like that is about $30 million. This data is free, completely free. And here's the coverage of the data. It's not quite global coverage, but it's getting there. No balloons over Antarctica, of course. Not much over Western Europe, Russia, India, not much at very high latitudes. But this is still the best geographical coverage and the seasonal coverage of any ballooning campaign to date. Some of these measurements have some pretty high error bars on them, but a couple of postdocs, Eric Lindgren and now Brian Green, have spent years on this data. They've combed through the data. They've done a wavelet analysis to isolate frequencies associated with atmospheric gravity waves. And voila, here we are. This is momentum flux. Because of atmospheric gravity waves, momentum transport by atmospheric gravity waves inferred from these Loon balloon observations. As you can see, there's parts of the Earth over which we have no data, but this is still just an unprecedented new data set from which we have momentum transport because of these atmospheric gravity waves. This is zonal meridional, top and bottom. And I should say that everything associated with this balloon data processing is publicly available through a Stanford website. You can go on the website, you can say you want to look at this trajectory from date X to date Y, and so where it went, the momentum fluxes, the Python script to calculate momentum fluxes, all of that is publicly available through a Stanford portal. And Brian and I, this paper, Brian and I are very happy to work with you on using any of this data if you like. We've only had a couple of papers on it so far, but I think there's a lot left to be done, particularly with respect to convectively generated atmospheric gravity waves. But okay, so that's one source of data. We are also working on some extremely high resolution observations to try and isolate momentum fluxes because of atmospheric gravity waves. I'm showing you just some snapshots from each of these. WRF is a regional simulation in collaboration with Chiang Sun. So this paper and his collaborator, his advisor, Pedram Hassanzadeh, we have a library of these WRF simulations to cover ocean, land, different latitudes, different phases of the QBO, MJO, whatever. So we have a library of these WRF simulations. We are running ICON. ICON is the icosahedral non-hydrostatic model, the German model. We are running this at something like 1.4 kilometer resolution globally, also building up quite a library of these. And we're also using the IFS Nature Run. IFS is the integrated forecast system from ECMWF. Also about 1 kilometer-ish. So here's an animation of some beautiful gravity waves of the Andes. This is about a year of simulation. No, it's not a year. It has to be less than that. Probably about a month of simulation from ICON, and that's WRF, just showing you some of these detailed atmospheric gravity wave structures. So we're attempting to put together all of these data sets to do both calibration and completely ML-driven schemes trained on these huge data sets, which you can imagine is a bit of a challenge. It's just the amount of data as a challenge. Yeah. So ongoing work involves calibration, like I talked about. So calibration can be not just calibrating on macrophysical climate states, such as what should the period of the QBO be. We could also say, I'm going to calibrate the actual momentum flux at 100 hectopascal in July. And I'm going to get the actual momentum flux from a combination of Loon and say ICON, something like that. So I can do that. I'm showing you, this is ICON, I believe. This is of the Drake Passage, Southern Hemisphere. This is in collaboration with Claudia Stefan at the MPI. Here's the actual drag that we're attempting to calibrate. So actual profiles of drag that we're attempting to calibrate. And I thought I should show you some, this is really fresh off the press. I think he made this animation 2 days ago. So transfer learning was mentioned in the previous talk. I think this is really exciting new stuff. So Aman, my postdoc, has taken ERA 5, estimated atmospheric gravity wave momentum flux from ERA 5, and trained an attention UNet on these fluxes. So here's the actual ERA 5 flux, here's his output. And having done that, we have then done transfer learning using these very high resolution IFS results. And by transfer learning, what I mean really is that we have retrained a couple of layers of the NN on this very high resolution IFS data set. And here's the result from that. So this is an attention UNet trained on ERA 5, transfer learned with IFS. Here's the result. And you can see that the fluxes that are coming from this transfer learning experiment are in some cases twice as high as ERA 5 can actually resolve. And here's the result. This is a fully non-local scheme. It's not just vertical propagation. We're taking into account all of the horizontal propagation as well. Aman has written a couple of papers showing that the non-locality is really, really important. This paper here is momentum fluxes from IFS, from this very high resolution data set. And this new result that I'm talking about, he's working on, we should be submitting before the end of the year, I hope, but then you never know. So, so here's the animation. So these are some really high resolution fluxes that have come from purely ML model, trained on Era 5, so it's got the nice large-scale structure, right? But it's also trained on this very high-resolution IFS run. And we're working on coupling the scheme back into the CAM Wacken model, the NCAR infrastructure. So I think, again, you should invite me back in a year because I'm going to have lots of new results to talk about in a year. All right. I don't know how I'm doing time-wise. I just wanted to mention this project that I've been working on for a couple of years. We called it Data Wave. They told us that we had to come up with a catchy name. Data Wave doesn't stand for anything. It's just Data Wave, but it's meant to encapsulate using lots of data to say something about atmospheric gravity waves and also improve how they are represented in these global climate models. I'm the PI on this project. It's funded by Schmidt Sciences. Used to be called Schmidt Futures, now called Schmidt Sciences. Here are all my co-PIs. I have 1, 2, 3, 4, 5, 7 of them in different countries. 4 of us are in the US, the rest are in UK, France, and Germany. And generally, if you go on here, we're either looking for a student or a postdoc or sometimes even undergraduate researchers. So we would love to hear from anyone who is interested. So we would love to hear from you. Please send us an email if any of this is of interest. It's going to combine, as I said, new observations, very high resolution simulations, and some data-informed methods, such as what I've showed you already, to try and improve both our understanding of atmospheric gravity waves as well as how they're represented in these global climate models. I am going to end there. I had a picture of the QBO at the end. Well, never mind. How do I... I'll go back to the end, and then I'm happy to take questions. So thanks for your attention, and please ask me whatever you like. I leave it there.
Audible?
Yep.
Yeah. So in your previous lecture also you mentioned about the gravity wave turbulence in the middle atmosphere influence the quasi-biennial oscillation. So can you elaborate more on that? Like the gravity wave turbulence are small scale and it is more intermittent.
Right.
Then how it's influencing the...
So what drives the QBO is the question. I can share notes with you on idealized models of the QBO, but the short story is that there are all of these tropical waves, including atmospheric gravity waves, Kelvin waves, other waves like that, which in the tropics propagate upwards and deposit drag. And it's a really lovely wave mean flow interaction problem, but they deposit drag, the winds change sign, and then the whole thing reverses. But it is a full lecture as to what drives the QBO. But that's the short story. It's drag deposition by waves, which changes the sign of the mean flow, which then changes the waves, which then changes the mean flow. But why don't I share notes? I think that might be a better,
I have one more question.
Sure, yeah.
So we can also use the data from LIDAR, right?
Use the what?
Data from LIDAR observation.
Yes. Yeah. So there is some observational constraints that can come from LIDAR, particularly about the vertical structure of stratification, things like that. But that does not give us in situ data like the balloons do, because the in situ balloons are observing every minute. That sort of time resolution simply doesn't exist in terms of other measurements. Satellites and LIDAR and so on cover a different frequency range of the spectrum. Question at the back.
Hi, Aditi. Really very nice. Very nice work. So this is more a philosophical question. You talked at the beginning about, and this does not apply only, I think, about gravity waves, parameterizations, but you talked about a little bit the difficulty of interfacing ML-based parameterizations with the infrastructure or climate model. And so I was wondering, should we give up, or is it part of what you guys are also working on? Should we give up on the idea that maybe this ML-based parameterizations might inform traditional parameterizations, and how is that conversation going or happening?
Right. The conversation seems to be proceeding along both lines that I talked about. One is having completely machine learning based parameterization, which I guess I'm a little bit less comfortable with than the second approach, which is let's use the ML to learn parameters. So there's an equation that we think holds. It holds in this climate, holds in a future climate. It just makes physical sense. It holds. But then there's a number in there which we're unsure about. So let's just use ML to learn that number or learn uncertainties in that number. So I think the conversation is proceeding along both those lines. Klima is using the ECI approach. I think they're quite committed to that, and the Bayesian approach is also sort of gaining traction a little bit. And then there's a whole other set of people who want to do completely ML-based parameterizations and are going through the struggle of integrating it into the climate model. And in addition to the Fortran Python thing, there's also the CPU GPU thing. Instabilities, yeah. And but there's a couple of new papers, very nice ones, sort of ML theory ones that have a framework to tell us which scheme is going to be stable and which is not going to be stable. The problem with that is that the model needs to be differentiable in order to say that. And there is a model that's come out of I forget exactly what the name of the model. It could be Neural GCM, I don't know, which is entirely written in I think it's Neural GCM. So there are ways forward. And I've heard of like workshops being proposed on the stability of NNs coupled into models, et cetera, et cetera. So I think there's ways forward in both of these. I am personally more comfortable with the let's use whatever methods are out there to learn this parameter. Let's just use, like whatever combination of data sets like we did with the IFS and ERA5, right? Let's keep the large scale structure, throw in a little bit more high resolution data and see what's our best estimate of this parameter. That's what I'm most excited about. But I think enough people are going into the purely ML thing that some progress will happen on that too. Uncertainties are going to be difficult. Stability, you can just cut the time step, things like that. But yeah, so it's work in progress. There's a lot of smart people working on it. So let's see.
Really nice talk. I'm interested in your intermittency term that you introduced in the second part.
Yeah.
Have you included any state dependence in that term, such that, for example, during QBOE, convection might be more energetic than QBO West? Have you looked at things like that?
Not explicitly what you said, but the Wacom convective, the gravity wave scheme that is dependent on convection is actually coupled to the convection. So when convection fires off, you also get a source of gravity waves. So we've tried to emulate that, and we're doing a pretty good job. So it's not explicitly what you said, but it's kind of what you said, and yeah.
Maybe I have a question. So
Sure.
my question is kind of what is maybe indirectly observable about gravity waves, which can kind of give a handle about maybe make a kind of converge onto a particular type of parameter.
Right. It's an interesting question. I mean, the QBO is something that is indirectly observable about gravity waves, right? Because if you don't have a gravity wave parameterization in a model, you don't get a QBO. And getting the QBO right is a function of tweaking the GWP. So the QBO is something that is indirectly observable about gravity waves, that tells you about gravity waves without actually observing gravity waves. So which is why we've kind of focused on that. I would have said that the polar vortex variability is also a function of atmospheric gravity waves, but you tend to not focus so much on negative results in talks. So calibrating based on polar vortex variability has led to mixed results, because there's this interesting compensation between planetary scale waves and gravity waves. So if you actually increase gravity waves, the planetary scale waves tend to compensate such that your result is the same. So when you're dealing with a system like that, it's hard. We're not actually sure what to do next on that problem. So yeah, Technically, the jet stream, like the position of the jet stream, the strength of the jet stream, how variable it is also a way to indirectly observe gravity waves, but it's also a way to indirectly observe other waves. So, yeah.
I'm not sure but if there is anything from the theory and which can be clubbed with balloon observations.
Right. So the theory is very well known. It's atmospheric gravity. So it's linear gravity waves propagating on a slowly varying background state. I teach it in a graduate class, right? Everybody understands the theory. It's not so much that the theory is a problem. The problem is a lack of observations, and the problem is a lack of explicitly modeled gravity waves. So that's what we're trying to fix. I mean, so if you have, so Loon, for instance, is great, but it only gives us like a specified region of the, so the balloons just kind of bob along, and they stay at a pretty fixed range of altitudes. So they don't give us profiles. So someone mentioned LiDAR, which does give us profiles, right? But that's actually very useful information, because you can integrate one and get, I mean, you can integrate flux and get drag. So having a flux at one position is actually quite useful. And combining it with all of these other high resolution data sets seems to be the way forward. The theory itself is helpful, and the theory is helpful in that you can put in something like 8099 into a model, right? Because that's based on theory, and that is true. The problem is fitting all of these other numbers that the theory doesn't tell us. The theory has been understood for a long time, yeah.
Any other questions? Maybe I'll ask one more.
Sure.
So in first part of your talk, you showed that U and V had the most projection. I was wondering, is there a structure you could recover in U that is informative?
Yeah, the U and V are most informative because basically the waves break when the phase speed of the wave matches the background flow, right? So that's why U and V are helpful. Actual gravity waves don't behave so simply, right? Because they also propagate horizontally. So the theory is not as simple as 8099. But yeah, we're trying to do some of the things that you suggest. Like, for instance, you can take ERA 5 profiles. You can say which ERA 5 profile gives us something that looks like Loon, right? Or like, what version of 8099 with an ERA 5 profile will give me something that looks like Loon. So we're playing those games. We'll see. Okay. Yeah.
Thanks. Well, if there are no more questions, let's thank Aditi once again.
Thanks, everyone.
Thanks a lot.